Ladies and gentlemen, please take your seats at this time. Out of respect for our presenters, we ask that you please silence your mobile devices.
Greetings, Bill Nye here, CEO of the Planetary Society, coming to you from sunny Pasadena, California. It might not seem like it at first glance, but this little town has been the birthplace of some of humankind's biggest ideas. Am I right, Cassie? It was here we discovered the ever-expanding universe and our place within it. And here we got up close and personal with our far, far away friends. Yes, like a powerful magnet, this little town in Southern California draws the brightest minds from every corner of the globe. While the city's past made history, its present writes humankind's future. Today, a new wave of brilliant minds carry the torch and with gazes fixed permanently upward, make it their mission to uncover the universe's greatest mysteries. Every day, fueled by a passion for progress, the creations of the curious, the experiments of the fearless, and the pursuits of dreamers come together right here to move us forward and change life as we know it. From NASA JPL to Carnegie Observatories to the Planetary Society to Art Center College of Design to Innovate Pasadena and to Caltech. With that much brain power all in one place, it's only natural that the innovative spirit spills into the air, inspiring all who breathe it in. Want to experience tomorrow for yourself? Come visit this little town cranking out big ideas. It's where great minds meet.
So I have a question. How many of you are residents of Pasadena? Raise your hands. I'm a resident. Oh, great. It's a good turnout. Wasn't that a great movie about our town? Absolutely great. And who was that science guy that we saw, right? Yeah, so for the 2 or 3 of you that may not know who he is, you'll meet him later in the program. So I think we're in for a very enjoyable evening tonight. My name is Tom Prince. I'm a professor of physics at Caltech, and I'm also the chair of the committee that put together the scientific program for this entire conference, including this public lecture. Since this is a public lecture, some of you may be asking, what is COSPAR anyway? So COSPAR stands for Committee on Space Research. It was founded 60 years ago, and it was founded right at the dawn of the space age. So the year before Sputnik 1, the first artificial satellite launched by the Soviet Union, came out in the year before, and then Explorer 1, the first US artificial satellite, was launched the same year that COSPAR was founded. Obviously, there was a lot of competition going on at that time. What was really needed was cooperation. And so COSPAR was founded to be the premier organization that promotes cooperation and coordination of space activities around the globe. It has 45 member nations, and of members and associates, it has 117 countries represented. So it's truly an international organization. The conference and COSPAR covers all of space sciences. So it includes Earth science and planetary science, lunar science, solar physics, heliospheric science, astronomy and astrophysics, et cetera, et cetera, et cetera. So it's truly a very broad organization. So every 2 years, members of COSPAR assemble for a major scientific meeting. And I just want to read you the names of the cities that have had the last few COSPAR assemblies. They are Paris, Beijing, Montreal, Bremen, Mysore, Moscow, and now Pasadena, and 2 years from now will be in Sydney. So for all of you Pasadenans, I think we're in pretty good company, right? So I think it's really a credit to Pasadena to be a major host of COSPAR. So over 3,000 individuals are attending this year's assembly here at the conference center. I want to welcome all the COSPAR delegates tonight, and you'll be able to tell them from others and their guests by the badges. But I especially want to welcome all of you from Pasadena or the locales around Los Angeles, and I want to thank you for your support and interest in space science and space technology. Without your support, you, the public, many of the things that we do and some of the great exploration that you'll see talked about this evening probably wouldn't happen. The list of people and organizations that I could thank for this conference is very large. However, I do want to especially thank personally 3 people and who have had special roles. So first of all, Greg Vane from JPL was the person who had the vision, there's Greg, for this initially, and was a guiding light throughout the entire process of putting our bid together and bringing the conference here. I'd like to thank David Imo, my colleague from Caltech, co-chair of the local organizing committee, and for 3,000 people, there's a lot to do. And then lastly, she may not be out here because she's always doing something interesting, and that's Laura Gordon of International Conference Services. Every time I turn around, I see Laura, and I think there must be 5 Lauras. Okay, so this is Laura Gordon, okay? And so however many Laura Gordons there are, I want to thank them. So a special thanks this evening is to the company Orbital ATK. And and here to welcome you this evening is David Townsend, founder of the Orbital Corporation and the former president and CEO of Orbital ATK. And the only reason he's former is that Orbital ATK was just acquired by Northrop Grumman. David was a graduate student at Caltech and is on the Caltech Board of Trustees, so that makes him a pretty good guy, in my opinion. So thank you, Orbital ATK, and David, where are you? Do you want to say a few words of welcome?
Thank you, Tom. On behalf of Orbital ATK, which, as Tom noted, is now the Innovation Systems sector of Northrop Grumman, I'm happy to welcome all of you to this evening's public lecture as part of the COSPAR 2018 Assembly. Tonight's lecture and the panel discussion that will follow it cover one of the most exciting and fast-moving fields of space science, the search for habitable exoplanets. In this area and many others, our company is proud to work on a wide range of space-based science missions that are helping to advance the frontiers of human discovery. In fact, during the last 35 years, we have been privileged to develop and build over 50 spacecraft for astronomy, heliophysics, planetary exploration, earth science, and life science programs. But one of our most recently launched satellites, the Transiting Exoplanet Survey Satellite, or TESS, is one of my favorites and one that you may hear about this evening. So now you're in for a real treat, hearing from one of the world's leading researchers in the exciting search for life elsewhere in the universe. Thank you all for coming, and enjoy the evening.
Okay, it's now my pleasure to introduce this evening's lecturer. Sarah Seeger of the Massachusetts Institute of Technology is a professor of planetary science, physics, and aerospace engineering, and she holds the class of 1941 professorship chair. She has pioneered many foundational research areas of characterizing exoplanets, with her present focus on the search for life by way of exoplanet atmospheric biosignature gases. She is the PI of the CubeSat Asteria, and CubeSats are small satellites, really small satellites. She's also the Deputy Science Director of the MIT-led NASA Explorer mission, TESS, which David just mentioned. And she is also lead of the Starshade Rendezvous mission, a space-based direct imaging exoplanet discovery concept that is currently under technology development. Professor Seeger was elected to the U.S. National Academy of Sciences in 2015. She is a 2013 MacArthur Fellow, and she has an asteroid 9729 named in her honor. She's also a great ambassador for science. She has appeared on CNN and BBC, and I think you'll really enjoy hearing her lecture this evening. So, Sarah.
Thanks, everyone. Thanks for coming out tonight. So I'm here to tell you about exoplanets and the nearest stars in the search for habitable worlds. I was wondering how many of you have been to a truly dark sky. Quite a lot. Well, the next time you go to the dark sky, or you can probably see a few stars from Pasadena, I want you to look up and to wonder what kind of planets are around that star. Is there any intelligent life, maybe, around one of the planets looking back at our sun and wondering the same thing? Because every star in the sky is a sun. And if our sun has planets, Mercury, Venus, Earth, Mars, etc., it makes sense that the other stars, other suns, have planets also, and they do. And we have evidence that nearly all stars, nearly every star, should have a planetary system. In my talk today, I'm actually going to give you my answer, for the questions I get asked most often. And I've listed the questions here. These are questions I'm asked by peer scientists, journalists, children, people, other soccer moms, and anyone really. And one of these questions actually I get asked most often. You can ponder that during the talk, and I'll let you know when we get to that question. So for the first question, what is an exoplanet? I actually encourage you to go home. Don't do it now, because I want you to pay attention. But when you go home later, you should Google eyes on exoplanets. And there's NASA software, you can download it. And it's really fun and instructive to learn about exoplanets. So I have a little clip, a little animation from this interactive software. And it begins with like a fake image of what we think our galaxy looks like. And it zooms in to a real map of the stars. The highlighted stars are stars that have known exoplanets. Hopefully you can also see the white stars out there. We don't know yet if they have planets. Now, the software, it's sort of showing you a picture of our solar system, but you can go to Earth, and from a spring or summer night sky from Pasadena, you can see, or any location, you can see what the night sky looks like. It'll overlay the constellations, and there's a very special patch of the sky that has so many stars with planets. Shout out if you know what it is. I didn't hear it, but he said Kepler. The Kepler Space Telescope stared at one patch of sky for 4 years. And the whole sky actually should be littered with stars with planets. Now, if you know any, you can type in the name of that star with known planets, and Kepler 186, the software, will take you to that system, and here it's showing you that there are 5 planets orbiting Kepler 186, and it will show you the zone around the star where the planet with a thin atmosphere is heated by the star, is not too hot, not too cold, but just right for life. Then if you click on it, here you have to read the fine print, which says hypothetical visualization of planet. We don't have that. I know the delegates will all know. We don't have that kind of image of an exoplanet. We won't for a very long time. But there you go. There's lots and lots of stars, thousands of them with known exoplanets. And for most of these planets, we don't know a whole lot about them. We know possibly their size or mass and their orbit. And actually, we really want to learn more. And I'm not going to dwell on all the different planet types, but I want you to know they're so crazy. We haven't yet found what we would call a solar system copy. Some systems have an Earth so close to the star that its temperature is thousands of degrees Kelvin, its surface hot enough to melt rock. And these hot super Earths would have surface liquid lava, not from volcanoes, but just from the heat of the sun. I mean, it feels pretty hot out there today, but these ones are way hotter. There's planets that were Jupiter where an Earth should be. And there's all kinds of planets of all sizes, masses, and orbits. So I like to say in exoplanets, anything is possible under the laws of physics and chemistry. Now, in exoplanets, rather than go into some tedious level of detail about how we know what we know, we love to speculate. And there's a series of NASA travel posters. The one I just showed you, that planet with the 5 planets, Kepler 186. And this is about Kepler 186f, where the grass is always redder on the other side. And Kepler 186 is a red dwarf star, which I'll come back to. And people actually, believe it or not, do write papers on what would photosynthesis be like on a planet where most of the light is in red. Now, are there any amateur astronomers in the room? And you know how, if you are, yeah, you have like a red flashlight at night probably when you're doing your observing, because you don't want to like blind your eyesight, get rid of your dark night vision. To me, that's what I feel like it would look on some red dwarf star planets. Everything just would be like in that reddish, bathed in that reddish light. Experience the gravity of HG 40307G, a super Earth. In this case, there are planets out there where we know their mass and their size, and we can get their surface gravity, and this planet has about 1.5 times Earth's surface gravity. It would be really hard for us to walk around on that planet. But here it's imagining that we go there and someone's going to be parachuting in the gravity of that planet. Relax on Kepler 16b, the land of 2 suns, where your shadow always has company. There are planets orbiting 2 stars, circumbinary planets. We know of a dozen or more of these, and there's probably way more out there. And I like to say in this case, science fiction got some things right. So what is an exoplanet? A planet that orbits a star other than the sun. Thousands of exoplanets are known to exist, and we expect and even have some evidence that nearly every star has a planetary system. So the next question is, when and how will we find another Earth? Is the set of questions I get asked most often. Well, let's talk about planet-star relationships, because a planet like Earth in itself wouldn't be fainter, or it may be as faint as the faintest galaxies observed by Hubble. The problem is that a planet like Earth, it's right next to a big, bright, massive host star. And I put some numbers here for you. I mean, our Earth is 100 times smaller. In area, it's 10,000 times smaller in area than our sun. Our Earth is 300,000 times less massive and 10 billion times fainter than our sun. So we always have to try to find another Earth in the presence of its star. We can't really get around that, actually, and that's the biggest challenge in exoplanets, in finding planets. So I'll put it to you for a moment. Which technique would you choose if you are working, and some of you are working on trying to find another Earth? Would you choose the one related to planet size? I'll see a show of hands if you would work. It's not a trick question. It's just like, do you want the easy way out or not? I mean, that's what it's about. Would you choose mass? One, because Earth is 300,000 times less massive. Would anyone want to choose looking for an Earth in reflected light, where our Earth is 10 billion times fainter than the sun? Well, the thing with exoplanets is the line between what is considered mainstream and what is considered crazy is constantly shifting. So just 10, 20 years ago, it would have been laughable to put your career on exoplanets. And I won't get to every technique, but just so in full disclosure, my favorite one is the one with the 10 billion times fainter. And so we'll get to that. But I just wanted you to see the lay of the land here and why it's such a hard problem. So it is true, if you voted for the first one, that's where the game is now. That's the biggest game in town for exoplanets. It's finding transiting planets. When the planet goes, some planets are luckily aligned, and they go in front of the star as seen from our telescopes. Can you see that little Earth going in front of this it's just an artist's conception. We don't see any stars spatially resolved like that other than our sun. But what astronomers measure is what's on the bottom in the little graph. We measure the brightness of a star as a function of time, just taking an image over and over again of a set of stars and looking for a tiny drop in brightness related to the planet-to-star air-hair ratio. And the artist here has added some noise in the data, which is good, because usually it's pretty noisy, especially for small planets with very small signals. Now I have a little note here. The Kepler Space Telescope, in its prime mission phase, stared at one large field of the sky with over 100,000 stars for 4 years, searching for a transit that repeated 3 or more times. All this data is archived. You can download it. You can go to a website called planethunters.org and look for planets by eye. And there's a lot of things that have been done with Kepler. It was like our big data, one of our big data entries for astronomy. So now there's a lot of work, actually, that goes once you have this light curve into establishing it as a planet candidate or just instrument noise or binary star or something else. But for what it's worth, just for a technical point for the delegates in the room, one of the reasons the transit technique is so popular and so great is because we can have a wide bandpass and take all photons. We don't need to split the photons up into wavelength bins, which we need to do for other techniques like measuring planet mass. And yeah, so planet, we can use all that, and there's thousands of planets found with this technique. Okay, so we actually even go further than that. If you thought that 1 part in 10,000 for planet area was easy, then here's an image of our sun, and here's a little tiny star, a red dwarf star. And this isn't a picture of TRAPPIST-1, but I put the name of one of the most popular exoplanet host stars out there, TRAPPIST-1, just to show you that there are some very small stars out there, tiny. And here I've put the same planet, I just cut and paste. But look how much more area the planet blocks out from that small star compared to the sun. A lot. And so for these small stars, we actually have planet to star area ratio of 1 part in 100. So it's just 1%. Instead of like our sun, where our planet to star area ratio for an Earth would be 1 part in 10,000. And the probability to transit, by the way, the further away the planet is from the star, the lower the probability is that the chance alignment works out in our favor. For our sun and Earth, that would be 1 part in 200, whereas for a small red dwarf star, a planet that's close to the star, so it's heated to the right temperature, not too hot, not too cold, but just right for life, is quite close to the star, and the probability would only be about 1 part in 30. So in astronomy, I don't know if we're like cheating or just we're definitely trying to take the easy way out. But there's this whole race to the bottom, smaller and smaller stars. That is where the whole field is moving right now. We're kind of trying to do the easiest thing first. And I just wanted to put it to you one more time about how this precision is. I mean, let's take example, you're gonna build a deck, an outside deck for your house. And let's just say, for argument's sake, it's gonna be 12 feet by 20 feet. When we talk about these numbers, 1 part in 10,000, that would mean that you'd be building your deck to 12.00001. Like, you would never do that. Or what about the 1 part in 10 billion, so many zeros. So these precision numbers are hard no matter what you do, and very few fields of science have to reach those numbers. So how many of you have heard of TRAPPIST-1? I'm sure it's like a lot, but if you haven't, I just want to tell you about TRAPPIST-1. Now here's the transit light curves for those of you that want to admire them and look at the y-axis, which is showing you the scale of the drop in brightness, and the bottom is just time. The x-axis is time from mid-transit in days. And you can see that they're all slightly different. There's a lot of information encoded in the transit light curve. On the right side, there's just a cartoon image showing you, look, our sun in the bottom right corner, and then the size of TRAPPIST-1, and then the size of Jupiter. And it's true that TRAPPIST-1 is so small, it's such a small star, it's so small and so cold that any smaller and colder, it wouldn't be a star. It would not be able to fuse hydrogen in its core and generate its own energy. Now, the people that did the survey, led by Michael Guillon, they purposely decided to go after the smallest stars so they could find small planets. And in their pilot program, they chose 20 stars. And exoplanets, we're just lucky. We often, like as a community, pick a problem where planets are bountiful. And they found this incredible system with 7 planets. And these planets are all about Earth size, give or take, actually. 7 of them. It's just breathtaking, actually, because in exoplanets, there's a lot we don't really understand, like the habitable zone. What makes a planet habitable? We think the atmosphere we know the atmosphere just like controls the surface temperature. It's like a blanket that keeps the heat in. But no matter how much we understand or how we get it wrong, surely one of the planets has to be in the star's habitable zone. So there's all the excitement about these M-dwarf stars. And so actually, my team and a lot of others, some people here and all around the world, make complicated atmosphere models of exoplanets around different star types. And we use the laws of physics and chemistry and borrow from decades of planetary science to try to understand what the planets might be like. But instead of boring you with some of the tedious details of that work, let me take you on a virtual trip to a planet around an M-dwarf star. First of all, not TRAPPIST-1 per se, but in general, there are lots of different M-dwarf stars of different sizes, ranging from 50% the size of our sun down to even 10% the size. And this particular example, an M-dwarf star, a planet around an M-dwarf star, it's just an artist's conception, but look how big the star is in the sky. The star, the sun, on this planet would be quite big. There's an artist's license to make the sky different colors, just so it's colorful. And it's quite interesting that the planets around these M-dwarf stars to be in the so-called habitable zone, where a planet with a thin atmosphere, as heated by the star, is not too hot, not too cold, but just right for life. The planet is quite close to the star. Unlike, imagine it's the campfire analogy. If it's a tiny fire, you need to stand very close to feel any warmth. But if the planet is very close to the star, the tidal interaction between the star and planet, this actually will make the planet go into its lowest energy state, which theoretically is a planet that rotates one time for every time it orbits. So it's 1 day equals to 1 year as the planet goes around the sun. It's like our moon shows the same face to Earth at all times, because it's in that same special low energy state after tidal interactions over millions of years. What this means for us if we're visiting this planet is that the star or the sun is in the same place in the sky at all times. So where would you choose to go on that planet? You could go where it's always night. That would be the astronomers, of course. Or you could go where it's always daytime. I would go to that special spot where the sun has just set, and I would see the green flash and just see it last, hopefully forever. Now that's not totally true, because if there's any dynamicists in the audience, they would get mad, because our moon even isn't perfect. It's not the perfectly same face. There's libration. It kind of wobbles around this equilibrium point a little, so that's not true. Now this planet is close to the star, and by Kepler's third law, it will be orbiting the star very quickly. So in this kind of random hypothetical example, that this planet we're visiting, the planet would go around the star in about 20 days. So if there's any children in the audience, the year is 20 days. Your birthday would be every 20 days. That's good for the kids, not so much for the parents. I don't think you could handle having COSPAR every 2 years in that case. Maybe your unit would be like a century or something. Now, on the other hand, visiting this planet might be a bad idea for us, because these M-dwarf stars give off flares, big flares, of high-energy particles. What kind of sunscreen would you bring? You couldn't be flipping out your phone all the time, because the high-energy particles would knock out the electronics, destroying the phone. And if there's any life there, maybe it's subsurface, like we hope Mars has. Maybe it's on the dark side. I'm not really sure. Now, another thing I just wanted to tell you about TRAPPIST-1 is that the Kepler Space Telescope, in its K2 phase, it looks at 80-day period chunks of the sky. And one of these chunks of the sky had the TRAPPIST-1 star in it. And what they saw in an 80-day period was 40 flares. And these flares, in visible wavelengths, they're like a rise in brightness. But you have to extrapolate back to higher energies to kind of estimate how much energy would be in the flare. Now, one of those flares in 80 days was a giant flare. It was as big as the Carrington event. How many of you have heard of the Carrington event here on Earth? Okay, so there's a lot of us people in the know, but for those of you that haven't, in 1850, when astronomers were first trying to understand sunspots, a British amateur astronomer, he was kind of a professional, but he had trouble getting a job, so his family brewery helped support his astronomy endeavors. And he was looking at the sun one day and saw some sunspots brighten. They kind of whitened around the edges. And a day and a half later, our Earth was charged. People saw the northern lights, the aurora, nearly down to the equator. At northern latitudes, people could read the newspaper because of the northern lights. Telegraph operators took out the batteries, and the telegraph still worked. Some of them were using their telegraph, and their hands got burned. What happened was during this flare, a small piece of our sun came off the sun and hurtled towards Earth. We happened to be in the path, and this part of the sun had a little bit of magnetic field embedded, which hit our Earth's magnetic field and induced a current. And our whole Earth just got charged. So if TRAPPIST-1 has, let's say in that 80-day period, it had 40 flares, and one flare was like the Carrington event, I don't think we should be visiting TRAPPIST-1. And I just told you that story because we actually don't know what to make of planets orbiting M-dwarf stars. We're doing it because it's the easy thing to do, but the environments are so crazy and different. We don't even know if some of these planets have atmospheres. Maybe the atmospheres have been ablated or eroded by this host star. There's other complicated factors of the star, and we're not really sure what's going on. So I wanted you to get that flavor of this kind of, I don't know, Jekyll and Hyde kind of view. We love M-dwarf stars. We're not sure if they have life. We have to look at them. Surely nature is kind, and exoplanets will continue to deliver. And that's where we're at right now. I'm not sure how I feel about these flares. Sorry, bro. So we want to find more of them, and we did hear a bit. We heard TESS mentioned several times. I just have a few slides to tell you about TESS. It's an MIT-led NASA mission, an all-sky survey to find planets transiting bright nearby stars. TESS actually is, let's say its observational strategy is designed to focus on M-dwarf stars as it observes a strip of the sky, a segment, for a month. And remember I was mentioning a 20-day period? Well, some of these habitable zone planets around M-dwarf stars will have periods less than a month. I just put a couple of technical details there. Here is a beauty picture of TESS from a number of months ago. This was at orbital ATK, now Northrop Grumman, where you see TESS that's just being finished off. I wanted you to see just the overall size of TESS compared to the size of a human being. Here they are just finishing it off. The solar panels got folded up. They were the only deployable. Those covers on those giant cameras actually came off before launch. But TESS has 4 identical cameras. Think of them as extremely exquisite, glorified telephoto lenses. They have giant baffle around them, which is why they look so big there. But the cameras themselves, the aperture is only about 10 centimeters, because TESS is focusing on the brightest stars. In exoplanets, photons are our currency. The more photons, the better, because we want to learn more about the exoplanets, and we need the stars to be close and bright, and that's kind of one of the purposes of the TESS mission. There was an absolutely spectacular launch on a SpaceX Falcon 9 rocket out of Cape Canaveral. It was this April, just a few months ago, and it was unbelievably beautiful. Those who have worked on projects, I just couldn't believe how exciting it was that this project I'd worked on, and by no means did I work on it for the longest of anyone, but it was just sitting there up in that little well, the big fairing, it looked little from far away because we were like 6 miles away and the rocket was like that big. But the plume was so bright. It was unbelievably bright. And TESS went up there, and thanks to Orbital and others, it's in its final science orbit. TESS is still in commissioning phase. It's going to be starting science operations soon. And I'm sure you'll be reading more about TESS in the news as the 2-year prime mission goes by. So here's an animation of yellow are predicted TESS stars as we zoom away from Earth in contours of, we have like 10 parsecs, that's like in tens of light years. Blue are the Kepler stars with known planets. Gray is other. And I wanted you just to get a flavor that Kepler and its prime mission focused on one part of the sky, and for various strategic reasons, the stars ended up being quite far away in relative terms, thousands of light years. Whereas the TESS planets, I'm going to show you that animation once more, are close because we want the nearest stars. And that's the whole motivation for TESS, is to look at all the bright stars spread out over most of the night sky. And we expect to find thousands of planets. And these planets will be so bright enough stars that many follow-up observations can be done to establish planet mass and eventually look at the planet atmospheres and things like that. So just those in the know, like we call the MIT sometimes, the mission TESS is the finder scope for the James Webb Space Telescope, because TESS will find a lot of candidates that will be able to follow up in detail. So here, just to put to scale how much of the sky TESS is going to look at, 1 degree, 1 square degree, it's about, if you put your hand out and put your finger up, that blocks about a degree. It might be closer to half a degree, but for argument's sake, let's just say it's a degree. And now the 1 degree is in the top corner. And this is one detector, one CCD detector, 12 square degrees. And this is, by the way, simulated data by Zach Berta-Thompson. It looks real though, right? It looks real. But each camera, so each one of those like mini telescopes, if you will, has 4 detectors. This is just one camera looking at this big field. And just for scale, there's the constellation Orion and how it would fit within one TESS camera. Here's a real image from TESS. This is like a beauty pic. It's available as a JPEG. And it's actually just 3/4 of one CCD and one camera. And I hope that you appreciate how gorgeous this is. There's the Coalsack Nebula. That star at the bottom, that's not diffraction spikes, it's just a blooming effect on the CCD, but that's TESS. So how will we find another Earth? We'll fast track by searching small stars for Earth cousins instead of Earth twins. We'll use transits, the most favorable planet finding technique. So that's one takeaway for you. So can we go there? This is the question I get asked most often. And even sometimes I'll give a talk and I'll explain why, not yet actually, that's the answer, that people will still ask. They'll ask over and over in the Q&A, and I bet we'll get a question about that. Well, let's talk about distances. Here's a real picture of our sun. How big do you think Earth is compared to this image of our sun? There's a hint actually on the, yeah. That's a sunspot, and that's about the size of Earth. Okay, now a more difficult question is how far away do you think Earth would be from this image? Put up your hand if you think an Earth, to scale with the sun this size would be where you are. I don't see any hands, but it's really hard to see with the lights, okay. Well, actually, it turns out that our Earth, it's about 100 sun diameters away from the sun. So if we take this and try to count 100 of them, that might be like the back of this room, actually. So there's big distances in between things in astronomy. Now, if this is our sun, where do you think the nearest star would be to scale here? Here's people saying San Francisco. So there's a trick. It's actually, let's call it New York. How far away we can get and still be in the USA. So distances are huge. The distance between stars is so vast. Right now, our fastest spacecraft, I believe it's New Horizons, but the Voyager spacecraft are also traveling fast at something like 20 kilometers per second. They've left our solar system. But it would take Voyager 70,000 years to get to the nearest star if it was even headed in that direction. So that's quite far. We don't have a way to get there yet. I've heard a proposal for mission that could be the interstellar probe, which might travel 5 times faster than that, closer to 100 kilometers per second, but it's still too far. Can we go there? Not for now. But, this is humans, we're kind of born for discovery. And so let's imagine for a moment we do find a way to travel at, let's call it, say, 20th the speed of light. Our nearest star is Alpha Centauri at 4 light years away. Imagine we could actually, let's just say we could travel at 10% the speed of light. So it would take us 40 years to get to the nearest star. And I was wondering if any of you would be willing, if there was a way to do that, would you want to go? Would you want to be the first person or people to go to the nearest star? I mean, there's always people who want to. It's just human nature. Now, if you're about 20 years old now, in your 20s, and I know there's people at the conference at that age, you'd get there when you're about 60. And so you have plenty of time left, if you can stay healthy, to be there. But what I forgot to mention is it's a one-way trip. So would you still go? I mean, yes, the obvious answer is yes. There are people who will still go, and that's, I think, why it's the most popular question. Now, it turns out that the seeds have been planted for traveling, a way to travel interstellar, not us as humans, but this project called Starshot. And what Starshot is, it's a concept with real hard money of $100 billion, $100 million, it's still a huge number, by Yuri Milner, a billionaire, who wants to see this happen and is planting the seeds for us as humans to dream about really having a way to get somewhere. What Starshot is it would be lots, probably thousands of little tiny space chips, not spaceship, space chip. And there's a part of one right there shown with the person holding it. And the idea is that these would be launched and would deploy a sail. I think it would be about 1 meter in diameter. And then a bank of lasers on Earth that would all be coherently working together with adaptive optics, get rid of our atmospheric turbulence effects on it. And they would accelerate very rapidly within, I guess, minutes, these little sails to 20% the speed of light. And thousands of these little things would be zooming towards another star system. And as they zoom by, they'll take a picture and send it back, because the sail also acts as an antenna. And what I love about the project is they list themselves the 19 challenges, although today I read somewhere it was 30 in a talk I saw. They'll put those out to you. Here are the 30 challenges we need to get. And the one that's most perplexing to me is actually this bank of telescopes, optical telescopes, because they have to have 100 gigawatts of power. And that's like, imagine 100 billion light bulbs, that much power. And I'm not sure who would give you the land to do this, because if a plane or something flies overhead, that would be toast. Anyway, what I like about this is planted the seed. And remember, I told you the line between what is constantly crazy and what is mainstream is always shifting in exoplanets. As we have this idea now that with real money behind it, people can work on these challenges and see how far they can get. So the follow-up question is, if we can't go there, why look? That's really a question. So people are disappointed. We can't go there. Why are we doing this? Well, you know what? Science fiction got some things wrong. Because in Star Trek, the Enterprise had to travel at incredible speeds to orbit a planet so that Spock could look at the planet and see if there was any habitable life forms there. Well, if they tried to make a science fiction movie about the real exoplanet scientist's job, it would be incredibly tedious. I mean, just like whatever all the other delegates do. You have recommendation letters to write and committees to be on, and it's like everything. The time you get to do research is really fun, but then you're just kind of isolated, thinking in your own little world. So that would be pretty boring, but we don't need to go to other worlds, actually. We have ways to study planets remotely with Hubble Space Telescope. We have large ground-based telescopes, especially VLT, and this is Gemini. I think this is Gemini South. We have large telescopes of the future. This telescope, 30-meter telescope, would be 30 meters in diameter, and there's also the European Large Telescope, extremely large telescope, and the Giant Magellan Telescope. And all of these things are funneling towards us being able to study planets. And in the search for life, in the search for habitable worlds, we need to study planet atmospheres. And now I just have a few kind of more technical slides to share with you. You don't have to understand this to understand the rest of the talk. But I wanted to tell you about atmospheres and how we study them. I'm starting with this picture of a rainbow. And you've all hopefully seen rainbow, but did you know that if you could look at the rainbow very closely, there would be pieces missing? Little tiny pieces of the rainbow would be missing. And here's a picture of our solar spectrum. It's like a rainbow, but not made by a raindrop, but by a prism inside a special instrument called a spectrograph. And here it is. Look at all those little pieces missing. What's happening is the atmosphere, in this case our sun's atmosphere, but also Earth's atmosphere, molecules and atoms absorb light. I like to think of it informally like the atmospheres and molecules, atoms and molecules take bites out of the spectrum. And each of these lines means something. Some of them are fat, some are thin, but almost nearly every line is identified and associated with a very specific atom or molecule. And based on the laws of quantum mechanics, there normally is a one-to-one correspondence unless you think about really big molecules. And that's effectively how we study exoplanet atmospheres. We break up the light into colors and look for these absorption features, molecules that are taking a bite out of the atmosphere. And I did want to give you the point that we need these spectra to understand the atmosphere. The atmosphere controls the surface temperature. Just like on Earth, we worry about greenhouse gases and our planet warming. Imagine another planet that has an atmosphere with 100 times more carbon dioxide than Earth, or 1,000 times, or other gases that are also big greenhouse gases. We don't know what they'll be like. Like Venus and Earth they are the same size and mass. And to any exoplanet technique that we have now that could see these planets, even when we do better in the future, they'll look the same to us, unless we can see the atmosphere and get a handle on the planet's surface temperature. And in the best case scenario, we aim to identify gases that might be produced by life. Gases like oxygen or methane or other gases. So in exoplanets, I've showed you this slide already, but on the left there, you can see a planet, an artist's conception of a planet going in front of the star. And the artist has made this atmosphere glowing. But I want you to have the concept of how we study most exoplanet atmospheres today. So just bear with me for a few minutes. Now, the starlight, when the planet goes in front of the starlight shines through the atmosphere. And just like shining a flashlight through a fog, we can measure what wavelengths make it through and which ones don't, thus extracting what's in the planet atmosphere. Now imagine there's a wavelength where the atmosphere is transparent. There's no atmospheric absorption. Then the planet is a certain fixed size. But now imagine a wavelength where the atmosphere is a strongly absorbing, then the planet looks a tiny bit bigger, just a little tiny bit bigger. And that's really the key behind the method, is that the planet looks a little bigger at wavelengths where the planet atmosphere is strongly absorbing. And so exoplanet astronomers look for that. And here's now a Wikipedia level plot showing you absorptivity versus wavelength. And what you can look at is that all these different molecules, methane, nitrous oxide, oxygen, carbon dioxide, water vapor, they all have a slightly different spectrum. This is showing you the absorption peaks of these different gases at this kind of cartoon level. And I want you to look at this one gas here. It's between 1 to 1.5 microns. It's a water vapor absorption feature. And now I'm going to show you some real data taken by the Hubble Space Telescope, but I want you to focus on that feature. That's that same feature. And what you're seeing here is the transit depth, the planet size compared to the star size, as a function of wavelength. And this planet looks a tiny, tiny bit bigger where water vapor is strongly absorbing. And in exoplanets, this is our claim to detecting water vapor on a hot giant planet. And you're supposed to just smile and say, wow, that is awesome. I mean, if this planet didn't have an atmosphere, this plot would be a straight line. And so I think you, all the delegates and the scientists in the room, you can agree with me this is different from a straight line. So that's water, and it's a combination band of water vapor, and everyone's really excited about this method. I wish I could, this is actually, there's an entire talk about this earlier today in one of the sessions. And I just have one more I wanted to show you. I don't have time to explain the details, but I want you to admire this. The data's not as good as many other fields, of course, but this is the best this field has to offer. And if you had time to look at the error bars and work out the details, you would see this is tiny, tiny, very highly precise measurements. But we do have a field of exoplanet atmospheres. There's dozens and dozens of exoplanet atmospheres been observed. They're not small habitable worlds. They're big, hot, giant planets. Some are small and habitable. Many of them don't show anything. We think they're riddled with clouds and hazes. That just like when you fly in a plane and you go above the cloud deck, you can't see the bottom, the atmosphere or anything. We think a lot of planets are just full of clouds that mask the spectral features. Okay, so I don't have time to talk about that. Let's see, I just have like about 5 more minutes, so let me wrap up here. I just want to tell you very briefly about my favorite project. Let me see if I can go back here. Right, so the problem is that we want to find signs of life on another world. We're hoping for oxygen because our own planet has oxygen that fills our atmosphere to 20% by volume. But without life, without plants and photosynthetic bacteria, we would have no oxygen. None, actually, maybe a tiny amount. And so that's, wow, we love oxygen, but our Earth didn't have oxygen for half of its life that we could detect anyway. And so we're trying to consider all possible gases, and my team literally stumbled across like this big data chemical space project. I wish I could tell you more about it. But we literally, just for whatever reason, enumerated every single gas, every single molecule that should be a gas at room temperature and pressure, to exhaustively search all kind of groups of gases all categories of gases by their functional groups, to search for anything, not to leave any stone unturned. So when we finally do get spectra of another Earth, we'll have like a menu of options to sort through what we might be looking for. Now I'm going to get to the last part of my talk, because transits and M-dwarf stars are only the first part of a very long story. Transits are limited to planetary systems with a fortuitous alignment. And I really do see these as transiting planet atmospheres. They're these Earth cousins instead of Earth twins. And I want you to think about this for a second. This would be like, imagine you go on 23andMe and you give your DNA and you hopefully find out you're healthy, but you also find out you have a cousin, a long lost cousin. Maybe it's someone of a different generation from a different country, they speak a different language. This actually happened to me, by the way. I went on 23andMe and it said I had a first female cousin, and it wasn't one of my 2 first female cousins. And I politely emailed, hi, I'm Sarah, can you please tell me who you are? And it was like this big mystery, I didn't know who it was. And eventually I found out, as other relatives started appearing, it wasn't a first female cousin, it was like a first cousin once removed, and it was like a lady in her mid-80s, and she wasn't from a different country, she was actually from California. She was was on her 4th husband. I mean, she wasn't that similar to me, but nonetheless, she was sort of related. But now I want you to imagine a case, but I genuinely hope this doesn't happen to you, it's just a thought experiment, that you go on 23andMe, and wow, you have a twin. There's someone who appears who is literally identical to you. And all of a sudden, you're able to understand that person and know pretty much everything about them. And that's kind of the dream I hold on to about finding the true Earth twin. And transits probably won't cut it because the planet is so small and the sun is so big, and that technique doesn't shine for that particular object. So we need a new way to do it, and I only can very briefly tell you about it. We call it direct imaging. We want to block out the starlight to be able to see planets directly. We won't be limited to stars that are fortuitously aligned. We can have sun-like stars, this actually method works for. And there it is, it's called starshade. And you can ask in a Q&A because I don't have time to explain why it's a special shape, but it has to do with diffracted light. Here's an animation of starshade, a way to block out light of a distant star, where petals will unfurl from their stowed position, and this truss expands where these petals snap into place. Now, to block out the starlight to 1 part in 10 billion, the petals have to be very precisely manufactured to something like 100 microns, and the petals have to be placed with each other to within respect to millimeters. And the starshade is tens of meters in diameter, and it would formation fly tens of thousands of kilometers from the telescope, all flying in outer space, far away from Earth's gravity. Well, I didn't hear anyone laugh about it. So by the way, remember when I was telling you about Starshot and the thousands of little spaceships, and then I was telling you how the line between what is mainstream and crazy is constantly shifting. And although starshade is still in the future, it's being worked on now, it is mainstream. And I want you to believe in starshade because my personal opinion is it's our best way we have to find the true Earth twin. There's myself and some team members at JPL with one of a petal prototype that was used to demonstrate that manufacturing tolerance can be met. Here's the Starshade lab at JPL. And by the way, Northrop Grumman also works on Starshade and has their own design. It's just to show you some scale models of, they call it membrane management, how the Starshade would fold up and deploy. Now to summarize, the search for habitable worlds. What is an exoplanet? A planet that orbits a star other than the sun. When and how will we find another Earth? Remember, the small stars, the race to the bottom, the smallest, coldest stars. Can we go there? Not for now. If we can't go there, why look? It's remote sensing to search for water and life. Now, what amazes me is that today, kids born, students in college, exoplanets were always around when they were around, and so the mentality that planets are known is just kind of accepted. Now, in the next decades, with the James Webb Space Telescope, once it's safely launched, hopefully with Starshade and other big projects, we have a chance to search our very nearest neighboring stars out to distances of, let's say, 100 light years and search their atmospheres for planets. But if that doesn't work out for us, if for some reason life is rare, or it doesn't produce big spectroscopic signals, then we have to wait for the next generation to come up with whole new paradigms. They'll need to find ways to build larger telescopes, ones that won't fit in any launch vehicle we can conceive of. We'll have to have manufacturing in space, perhaps giant 3D printed structures, and larger telescopes on the ground that we don't yet know how to fabricate. And perhaps even longer, in thousands of years or hundreds of thousands of years, we will have a way to travel to other stars, maybe not as ourselves, but maybe as post-biological intelligence or raw biological material that later gets printed out as humans. I wanted to just leave you with some crazy thoughts for the future, as I know COSPAR has the life sciences branch, and we just want to dream about exoplanets, and that's the gift of exoplanets. It allows us to think big and to really think beyond. Thank you so much for your attention.
So Sarah, thank you for a wonderful, wonderful talk. Really enjoyable. So let's see. So now I'd like to call Rosalie Lopez up to the podium. So I've had the privilege of working with Rosalie over the last 4 years to put together the program for the COSPAR conference. We've worked together as co-chairs of the program committee. Could actually give you a long list of accomplishments of Rosalie, but I'll leave you just with one intriguing one, and that is she is the human who has discovered the most volcanoes of anyone. Active volcanoes. Okay, she has discovered more active volcanoes than anyone than any other human. And as a hint, of course, they're mainly not on Earth. So Rosalie, please.
Thank you. Thank you so much. I would like to introduce now our panel, who, along with Sarah, will answer any questions that you might have. Could I call Dr. Bethany Ellman? Bethany is a professor of planetary science at Caltech and also a research scientist at JPL. Her expertise is in the mineralogy and chemistry of planetary surfaces, particularly Mars. And she's a member of the science teams for the Mars exploration rovers, the Mars Reconnaissance Orbiter, and the Mars Science Laboratory Curiosity. And I'd now like to call Dr. Cynthia Phillips. Cynthia is a planetary scientist at JPL. Her expertise is on the geology of icy moons, particularly Europa. She was an affiliate of the imaging team on the Galileo spacecraft, and is Kevin Hand's deputy on NASA's Europa Lander mission concept studies. Kevin unfortunately could not be here, but Cynthia can answer any questions about the Europa Lander. And our last member of the panel, I'd like to call Dr. Christophe Sautin. Christophe is the chief scientist for solar system exploration at JPL. His expertise is on the interior structure and dynamics of the Earth, Venus, Mars, and large icy moons of the solar system, but he's also an expert on exoplanets. He has been a member of the science teams on the Cassini spacecraft and also Venus Express and Mars Express. And to moderate this very illustrious panel, I would like to call the CEO of the Planetary Society, someone who needs absolutely no introduction, Bill Nye, the science guy.
Greetings, greetings, ladies and gentlemen, boys and girls, kids of all ages. It's great to see you. I want to start with, first of all, thanking everyone for taking the time, and thank you all for coming in the evening. I know many of you have been at conference all day, and it can take it out of you, but thank you for sticking around. And I hearken to the words of the previous U.S. president, who pointed out, well, I'm not kidding, he pointed out if you didn't have any control over where you would be born on the Earth, I mean, in this case, we're going to say we're being born on the Earth. We'll just start there. This would be the time you'd want to be born. This is the most exciting time in human history. And this is really, no matter what else is going on, this really is the most optimistic time in human history for the most number of people. And so, as I say all the time about space exploration, it brings out the best in us. Solving problems that have never been solved before, creating structures that have never existed before, and finding out more and more about the cosmos and our place within it. That is all thanks to you guys and gals. And so, thank you very much for your good work. And as you may know, I'm a mechanical engineer. I'm human, but I'm a mechanical engineer, and I finished my engineering requirements when I was at Cornell University, and I attended Cornell because of a marvelous clerical error in the admissions department. And I finished my requirements, and then I took one class from Carl Sagan for fun. And then his kids, Sam and Sasha, watched the Science Guy show. For those of you not from the States, it's a television show for children to get them excited about science. And then I was asked to be on the board of the Planetary Society. And then I'm sure this has happened to many of you here. I left the room for a few minutes at a board meeting, and now I'm the CEO. So what we do at the Planetary Society is connect people to space. We are now 38 years into this. And so if you're a researcher and you want to get the public excited about your work, please consider working with the Planetary Society. We have world-class journalists. We have access to extraordinary engineers. We're building our own solar sail spacecraft that will fly again sometime after October 30th. That's when the launch period starts, and we're on the second Falcon Heavy. And if you haven't seen the Falcon Heavy launch, it is amazing. Falcon 9 was cool. The Falcon Heavy's 3 of those. And then we have now 3 people that work full-time with the world's largest space agency, NASA, to influence policy, and we've been successful. We've gotten the NASA planetary science budget over $2 billion a year. So we are here for you, man. But as we like to say, enough about me. Let's get started. Does somebody have a chair? Do we have a chair? Because, guys, it's just a little weird for me to be standing up while the people who are providing the cool information are sitting. So, yeah, let me just take... I'm sorry. It's still funny for me. Let me go. I'll sit over there. Yes, on a talk show. Oh, here, we have a chair. Yeah, we have a chair. Oh, we have a microphone. Heck, wow. This is Richard Chute, our development director. He's our guy. All right, you all are not quite in what I hoped for the right order. Sarah, you're the farthest from the Earth. Then Bethany, you're at Mars, just 1.5 AU, it's right there. And then Cynthia, you're Europa. And Christoph, you're Mars again. You're anywhere that they have geologic processes. But with that said, Sarah, do you have a favorite place that you want to explore?
Well, my favorite place, which I'll call my favorite planet, it's actually always the next planet that's discovered, because there's always a better planet out there.
The next planet is your favorite?
Yes.
Unnamed, unnumbered yet?
Yeah, the unknown, that's right.
Cool. So how often do we discover a next planet?
Well, they come in spurts depending on the data and the technique. So we're in a bit of a lull right now. I mean, every time Kepler has a new field, there's maybe a few dozen new planets. But with tests, we'll have many more.
So a lull is what, at 2 years?
It's probably just a few months, actually.
A few months.
As Kepler is now in a bit of a hibernation mode, ending its mission, and TESS is going to start ramping up.
So stand by for Dr. Sega's next favorite planet. And then you guys, we can all make cool posters. No, it really is just, it's extraordinary. You know, the thing about science fiction, everybody, quite commonly, in a talk about this sort of thing, there's a reference to Star Trek. And the reason the Star Trek franchise has lasted so long is because it's this optimistic view of the future with science. So thank you. Okay, now, this is just revving up. Bethany, your favorite place? I mean, other than Earth.
Well, I have to say, just listening to Sarah, I think it's great that kids no longer have to memorize all the planet names, because that would get very challenging.
186F, 186G, 180.
There you go.
You could be at it a while.
Maybe it's easy. Keep going. Well, I have to say, you know, I'm going to give maybe a surprising answer. At the moment, my favorite planet is Earth, because it's so amazing for the only life forms that we know of in the universe yet, which is ourselves. But we're looking for where the rest of them are. And I'll say that one of my favorite places to look is Mars.
Why is it one of your favorite places?
It's one of my favorite places because, okay, so we had the analogy of twins and cousins. Well, Mars is maybe like the little brother that has had kind of a rough time of it, because it was, the more we look at Mars, it was once warm and wet and had habitats just like Earth. but they're not there anymore. So something happened to Mars, and there's still water in the subsurface, so there may still be life, but I'm really interested in what that means in terms of how planets work. How do planets like our Earth work? How do they sustain life through time or not? And is there life on Mars? So those are some of the reasons I think Mars is cool and worth exploring.
Now, speaking of cool, Mars is cold.
It is. I meant that literally, too.
Yeah, and so do you expect to find some sort of microbial something or other below the sand?
You know, I think so. I think if you were on Mars right now and you were like the smart life on Mars would be underground, right? Out of the extreme temperatures of the surface, protected from radiation, where there might be small amounts of liquid water, that's where you'd hang out. So that's one of the key places to explore.
So these would be things that cold, but if I may, for us humans, imaginably cold, right?
Imaginably cold. I mean, actually, the surface temperatures on Mars, if you're a rover or a human standing on the surface of Mars at midday at the equator, it's actually, about 20, 25 degrees Celsius, which means, nice 60, 70 Fahrenheit, pretty pleasant.
Cool.
Except for the fact that there's no atmosphere you can breathe.
Yeah, that you would notice that.
Details.
And for the kids out there, I just want to say this whole idea that we're going to go settle Mars, it sounds cool or cold. But it's not like you ever go for a walk. I mean, you'd live in a dome, and then when you go outside in your spacesuit, you're in another dome. You're like Sandy the squirrel on SpongeBob. I mean, you got to have the thing. So Mars is cold, but Cynthia, Mars is a joke cold-wise. Your favorite place?
Yeah, my favorite
Get a little closer,
place,
yeah.
My favorite place is Jupiter's moon, Europa. And Europa is this body, it orbits Jupiter, it's about the size of Earth's moon, but the surface is completely covered with a layer of ice. And so, we're talking about Mars, it's a bit chilly. Europa's surface, it's about 200 degrees below zero. So it's really cold. And Mars has kind of a thin atmosphere. Europa has basically no atmosphere at all. There's people who study Europa's atmosphere, and it's really like 6 molecules kind of in orbit around Europa, and they're saying, oh yeah, look, there goes one, look. So I like to call it a vacuum. That's kind of what we call that kind of space, but there are people who try to study this as an atmosphere.
Okay, now hang on. Fundamental question then, for people who may not be hip to this idea. How then could there be twice as much ocean water on Europa as there is on Earth? Why isn't it all frozen solid? Take it, Cynthia.
That's the really cool thing about Europa, is that we have this huge, thick ice layer at the surface. It's about 10 kilometers thick or so. And under that ice layer, could be thicker, could be thinner, probably thicker in some places. But under that ice is this huge global ocean. And yeah, like Bill said, there's twice as much water as all of Earth's oceans. And it's a real puzzle because the surface is freezing cold, there's no atmosphere, you're 5 times further away from the sun than we are here on Earth. So the sun, it kind of looks like a bright star in the sky. It's not going to be this huge glowing, life-giving orb like it is here on Earth. So it really was a puzzle as to how all this water could be there and how it could be liquid. And it turns out it's because of tides. It's because of Jupiter's strong gravity. It tugs and pulls on Europa as it goes around in orbit, and as it lines up in its orbit with 2 of the other satellites, Io and Ganymede. So Europa's going around, its orbit gets tugged on, it gets stretched and pulled and squeezed, and that's enough heat to keep all this water liquid. And so I think that, forget some little cracks on Mars that have little bits of ice maybe kind of sitting around there. We've got a huge ocean. You can go swimming. It's a gigantic swimming pool. So, if you're going to look for life, you got to go to Europa.
And so speaking of which, Europa!
Yeah.
So everybody, if you have ocean water for 4.5 billion years, it's very reasonable to me that there are some Europanians, right?
Yeah, not Europeans. We're talking about...
No. But we have some here.
Yeah.
And so, are there Europanian fish people swimming around, speaking Europanian? And do they, I paraphrase, and do they have like a whole nother completely different idea of the sky? Because it's ice.
I would love for there to be, giant squid in Europa's ocean with eyes the size of dinner plates, but there probably aren't. When we're talking about life on Europa, we're probably talking about little tiny microscopic microbial life.
Okay, but you have a plan to go check them out, right?
Yeah, you got to go and look. So we're working on a mission to go and land on the surface, and then maybe someday we can actually look in that ocean.
So we're going to send the Europa Clipper, yeah?
Yeah, the Europa Clipper spacecraft is currently being built by NASA. It's going to launch in about 4 or 5 years now, pretty soon, and it'll go and it'll orbit Jupiter with a whole bunch of close flybys of Europa to take the best close-up pictures ever. And, it'll look for things like whales kind of breaching, but, probably it's not going to see those. But it's going to study the surface, and it'll look for plumes of material ejecting off the surface, and it'll give us our best idea so far as to what's going on in Europa.
So everybody just appreciate, and I try to get this every day, appreciate what it would be like for humankind if we found evidence of life on another world. It would change the course of human history. It would be something akin to the discoveries of Copernicus or Galileo or Johann Kepler. It would just be, it would be utterly astonishing. Everybody would think differently about what it means to be a living thing in the cosmos. And we do this globally with the help of COSPAR. We do it for, pick a number, 3 billion euro, $3 billion a year. And the people who are going to make these discoveries, or let's say this discovery, are probably right here on the stage, and they work with their colleagues who are going to make those discoveries. Now, speaking of plumes squirting into space, Christoph, you're all about Enceladus, yeah?
Actually, I was thinking about your question, and I say, which one do I prefer? Which planet?
Yeah, what's your favorite?
It's a tough question, actually, because I think in order to understand how life has emerged somewhere, it's important to compare the different places. And there are 2 places I really love. It's Enceladus and Titan. In addition to Europa.
You can cheer for Enceladus, yeah, give it up. So tell everybody, because there's members of the public here, just remind them of Enceladus and Titan.
Yeah, Enceladus and Titan are 2 satellites of Saturn. And when we launched Cassini in so many years, I think it was 97. Sorry.
97, yeah. For those 1997.
Yes, 19. That was last millennium.
One of the disappointments, during the Adams administration, in the 1820s, the planets were lined up really well for a flyby, and they didn't do.
Yep.
They did nothing. Enceladus. It's a reliable joke. It's a good joke.
It's good, yeah. So Enceladus is very small, 100, well, I speak in kilometers.
Yeah, kilometers, yeah, we can do that.
Yeah, 100 miles, just imagine, radius of 100 miles. So very, very small. And everyone thought that this world would be completely frozen. I mean, it's 70 Kelvin, so minus 200 degrees Celsius on the surface. How can you imagine that this world is alive? And as for Europa, tidal, the tides are so strong on Enceladus that we discovered geysers coming out of Enceladus. Actually, Enceladus is the only place in the solar system where the ocean is coming to you.
So it's squirting ocean water into space.
Yes, that's what it's doing. And Cassini was just amazing in flexibility in terms, the project, because we first observed that, and then we decided, well, we need to go back, and the engineers at JPL and the scientists on the different instruments, they were able to demonstrate that you have this ocean beneath only 6 kilometers of ice, so very close to the surface of Enceladus, and you have those fracture zones, and they open and they close as Enceladus is orbiting around Saturn, and when they open, the water vapor comes out.
Are they, if there are living things there, are they Enceladosians?
Maybe.
So
I mean,
do
I
they
cannot say that.
Are there Enceladosian, grim jokes about, I sure hope I don't get near one of those guys or get swatted in the face? So,
yeah, I mean, if you're pretty nasty, I'm pretty sure they are sending them to this.
yeah, it would be
yeah.
very troubling. So, getting thrown into space, a giant geyser. So, this means, if I understand it, there are certain molecules that, like Dr. Seeger, there are certain molecules that are well suited for being associated with living things. Then is it reasonable? I mean, I know Enceladus is right, compared to what you look at, it's right here. It's why even bother? But there's got to be something to be learned about astrobiology from both the atmospheres that you look at and the stuff that's squirted into space at Enceladus. No? What are those molecules?
Well, there's a whole list of them, and it's more like we need to see the data and then infer what's there rather than being like a really great predictive.
But what is there one that's, or are there 5 that are especially intriguing?
Sure. You mean biosynth gases that
Yeah,
may be
yeah.
made by life? Yeah, made by microbes. I mean, we have like oxygen and methane and nitrous oxide, and we have, hydrogen sulfide. Many of these gases, unfortunately, also have other origins, like geological origins. So we really have to look at the context of everything together.
Well, I'm hopefully hopeful that you guys are going to find some evidence that there might be something alive there, and then we really want to send spacecraft or build the instruments we need to find these things, and that takes the support of people around the world who have a sense of how extraordinary such a thing would be. As I keep saying, life in my lifetime. So what we'd like to do now is take questions from the audience. And so there's 2 microphones, I believe, set up somewhere. And so if anybody's got a question, please bring it on. Here comes a running person.
Whoa.
Running person, yes, please, lead on.
Yeah. Hello. Dr. Seeger, what do you think is the best we can do to measure the density of terrestrial exoplanet atmospheres, the order of magnitude of their atmospheric densities?
Well, I'd say about to an order of magnitude, unfortunately, right now.
What do you mean by an order of magnitude in this case?
Well, let me think. So, I mean, the question is like, if we were to go to another planet, will the atmosphere just crush us? Or is it something that's going to be breathable that we can identify? So whenever I showed you the data, the real data of the hot giant planets, the best we could do in the future would be data that looks like that for another Earth. And it'll be hard to measure like the surface pressure and the density, although I don't have an exact number, so I just kind of threw something out there.
Okay, so
Terrestrial. I know in the future when we have data on terrestrial planets, it will be quite challenging to estimate the density of the atmosphere.
So my understanding is people estimated the density of the Venusian atmosphere with radar. Is that a true fact or a false fact?
Let's turn that to...
False fact's a joke, really funny. So like Mars is 7, what we used to call millibars, hectopascals, yeah?
Well, I mean, I don't know. You can't take a full stab at the question. It's a challenging question. But we want to know how thick the atmosphere is. We might want to know how much of different gases are there. So Sarah was talking about spectra, right, and lines and curves. And so at certain pressures, those spectra have different characteristics. So there's a certain pressure dependency of what those particular spectra and features look like. If the atmosphere is really thin, they'll have a certain shape, position, and depth. If it's optically thick, it could be quite different. It's complicated, though. Atmospheres are complicated and cool, which is why your sophisticated models are needed, because things like clouds get in the way of all of these determinations. So yeah, it's an interesting question.
But we'll have to work on the details and get you a better answer. Let's hope before the next COSPAR meeting.
Okay, but let me ask you this, with, a little knowledge is a dangerous thing. So let's say the Earth is 1 atmosphere pressure, 1,000 millibar, 1,000 hectopascals. Then Mars is a 100th of that. And Venus is about 100 times that. Are you saying you could get in between those 2 numbers with the techniques we have now. Is that accurate?
We might be able to say that.
There you go. Somewhere between Venus and Mars. Done. Boom.
That's not the helpful answer for him, because he wants to know, I'm not a mind reader or anything, but the question is there a planet out there somewhere we could go to? We couldn't leave with the pressure of Venus's atmosphere, nor could we leave one with Mars. So we're working on it, hopefully.
We'll get back to you. Yeah, 2 years. Yes, over here, sir.
Hi, my name is Juan Pablo del Toro. I'm a Jesuit priest. I know, weird combination, but I'm also an astronomer. And I teach science at our school in Phoenix. And I'm wondering if with all this data that is going to come out from TESS and Kepler, how is it going to be processed? Like, how many people will be needed to process all these transits that are going to come out of these space missions? And if you need more people to do it, that you can recruit through like Planet Hunters or some other software that we can do, because my students are always asking for more things to do.
Okay,
so
wonderful.
I'm wondering if we can give some extra credit for them.
Okay, yes. Well, TESS is very focused on its success of delivering. We have, like in NASA speak, it's level 1 requirements, and the team is focused on finding what TESS is supposed to deliver is 50 planets that transit with measured masses. But aside from that, there's certainly whole space out there. And to answer your question, the TESS team itself won't be putting it on planethunters.org, but I'm very confident that the data will eventually get there. And the human eye still does better in many cases than the computer. And
Why
so
is that? A human eye, a human brain does better than our best software?
Well, for planet finding, it's actually quite an interesting problem, because as you all know, I'm sure for the programmers in the room, I mean, the computer does what you tell it to do, but it can't look for something that you don't understand what it is actually. And even when there's signals, the most interesting planets, they're very noisy, like the signal is kind of barely there. And the computer will have a metric, like you can tell it exactly what you mean by a signal that's worthy of further inspection. But your human brain can somehow still pick things out that are unusual better than the computer can, because we haven't figured out how to instruct the computer to look for unusual things that we can't define in advance.
So go ahead. You need a bunch of grad students. You need
so we need a bunch of grad students.
Hundreds of.
But also the data is actually, technically TESS has no proprietary time. And as soon as all the wrinkles are ironed out, the data will be made public, like it'll be put on MASS, the archive where all the Kepler data is. So the students should get used to downlinking the data that is there now from Kepler, because it'll all be in the same format.
So can people be trained to look at that data and try to find?
Yeah, people can be trained using standard techniques, and keep your eye open for summer schools or winter schools where they teach this kind of thing, because they should be able to, with existing code or code they can write, search for planets and look for other things.
Excellent. Thank you.
Thank you. Over here, man in plaid.
Oh, thank you. First of all, Mr. Nye, I just visited the Planetary Society today, and I just joined. So
Thank you.
Thought that was uniquely appropriate to come tonight.
We're well over 50,000 members, and we want to get to 75,000. So check us out online. It's barely $4 a month. Do I care about me? No. It's you. You. So with that said, you have a question.
Yes. So my question is for Dr. Seeger again. So in terms of, I want to know what the likelihood and how you would approach finding the exomoons. So I know that would be probably an order of magnitude more difficult than finding an exoplanet, but perhaps something Earth-size around one of those hot Jupiters? I don't know, maybe a special exception, you could find an exomoon. Is that realistic?
That is a great question. And exoplanets is such a great field because we have our wish list, and we've gotten almost everything on it so far that technology can deliver. But moons are one thing. We should have found Earth-sized moons if they're out there with Kepler, because the data is so exquisite. And so far we haven't. And there may be like one paper on a kind of quasi-candidate moon that may or may not be anything. So it might just be that big moons just aren't there. We don't know for sure, but we haven't found moons.
Would we be looking for wobbles in the motion of the transit?
We could do that. So if the moon and Earth, or if a moon and a planet are orbiting the common center of mass, the transit will shift a little. Let me see, its duration will change slightly. But more easily would be to look for a little, like imagine you have that drop in brightness that's followed by a tiny, tiny drop in brightness. You see the little
so if you happen to catch the moon while it's in the plane to the what
Yeah.
I would call the left or right or the up and down.
Right.
Right.
It should be there, as long as it's not hidden behind the planet. We haven't found them.
Okay, do you know what paper that is, or should I talk to you after? I don't
Let
know.
me think. Well, the author would be Kipping, Kipping, David Kipping. He's associated with that. And you might want to contact him. I'm sure he'd love to answer a question about where we're at in that.
Okay, thank you very much.
That is a really cool question, the moon of the distant planet. Yes, sir.
I have a quick test question as well. Given that any other organisms that would exist out there would have a fighting shot of detecting us in the ecliptic plane using the transit method, why is it that TESS's scan architecture has skipped the ecliptic aside from noise floor issues and JWST ease of acquisition?
You mean has skipped our ecliptic?
Yeah. So the 4 cameras scan the northern hemisphere, the southern hemisphere, but both strategies skip the ecliptic plane.
Right, it's a good question.
And multiply image the polar squares.
Right. Like, I don't actually know the historic reasons to why that has happened. It might just be because of the moon and other planets that are really bright, our moon causing problems. But we're hoping, of course, like all missions, there's an extended mission. And there's no reason why we couldn't look at the ecliptic later. And hopefully that might be one of the options for the extended mission.
So twice, 2 in a row, she said, that's a good question. This is exciting, you guys. Over here, please.
Yeah, hi. I was wondering, while there's these missions in progress to land on places like Europa and perhaps other potential areas for habitability in the future, I was wondering if there were any corresponding advances in development for planetary protection procedures that are in the works to help mitigate unintentional contamination.
Thank you. This gives another opportunity to talk about the Planetary Society. So I really appreciate it. There's 2 things that I want, and we want, is to find life in my lifetime or somebody's lifetime, and then to keep the Earth from getting hit with an asteroid. So we work very hard to advocate, especially in the U.S. Congress, for missions to look for asteroids. You can break it down a number of ways, but let's say there's 3 ways. We want to detect them, we want to understand them, we want to get them, and then we want to deflect them. And so all this is probably possible in existing budgets. Budget's the key. And so we just want to have, I guess it's sort of a pun, a targeted funding scheme where we logically pursue this. It's a very, very low probability event, but very high consequence. There is no evidence at all that the ancient dinosaurs had a space program. And if they did, it wasn't good enough. And so, people talk about mitigation. Like, oh, we'll just mitigate the effects of the destruction of Tokyo. Yeah. No, we got to not really ever get hit with anything big. And so this is one of the big issues at the Planetary Society. And it's really an education, hardware or creation issue, and a advocacy. Being at ESA, NASA, Canadian Space Agency, JAXA, and advocating for a worldwide effort. Because although the cost of any search would go up, the cost per agency or taxpayer in any country would go down overall. That's a great question. And by the way, there's certain missions where the solar sail would be ideal, where you'd be in inferior orbit.
The other aspect of planetary protection, and I'm not sure which way your question is going.
You said planetary protection, and I went off on planetary defense.
Oh, good.
I'm sorry, you guys. That's my fault.
Well,
I've been on a plane. I'm dehydrated. That's my mistake. Totally my mistake.
Depends on which planet you wanted to protect.
No, my mistake. But it was interesting to me. So. Panelists, please take over. I apologize. Thank you.
Well, for those of you in the audience who, what are we talking about? Planetary defense protection, isn't that the same thing? Well, sometimes. So planetary protection, refers to specifically trying to, for example, when we search for life on Mars or Europa or Enceladus, not contaminating those areas with Earth life first, And conversely, when we, for example, bring samples back to Earth, not contaminating or possibly threatening Earth with life from other places. And so to answer your question, yeah, it's an ongoing debate and question as to, well, what are the best things to do for planetary protection? And how do we explore, right, explore boldly, seek life, while still managing the demands of not having all this cross-contamination happen, but not be so strict that we can't do anything, right? So this is the tension and the balance. And, you know, I can say a number of people in the Mars community are really excited about doing deep drilling to search for extant life. In Europa, this is a key issue. How do we keep the spacecraft clean enough for both drilling and like investigating on the surface? And I'll say, yeah, there are lots of efforts afoot. I'm not sure of all of them. I can say that for sure. I know that the new planetary protection officer at Lisa Pratt is like taking some of the new kind of burgeoning biotech, genome sequencing, and other more sophisticated aspects to deal with what is on the spacecraft now, who is actually there, how do they survive, how are they metabolizing, to really understand that forward contamination of other planets better. So that's one thing I'm aware of that's happening now, is kind of proteomics and genomics and moving planetary protection into a kind of predictive model for how these organisms that are actually present on spacecraft, even when we think we've sterilized them, might react. So I know that there are some efforts afoot that are trying to enable that, and I don't know if you want to add anything.
Yeah, and so for the case of Europa, obviously it could be one of our best places to find life in the solar system, and so the last thing we want to do is to kill off that life in the act of trying to detect it. That would be, you know, a big tragedy. So when we're talking about even just flying by Europa, like on Europa Clipper, the Europa Clipper spacecraft, it's not intended to crash into Europa, but something could go wrong. And so the spacecraft itself has to be very highly sterilized, but also you have to anticipate what are you going to do at the end of the mission. And so we're going to have to crash Europa Clipper probably into, you know, either Jupiter or maybe Ganymede or Callisto. We're still looking at some options. When we're looking at something like Europa Lander, where you actually land on the surface of Europa, you don't have that nice option of just kind of getting rid of the spacecraft when you're done, because when the Europa Lander spacecraft is done, it's going to be sitting on the surface of Europa still. It's not going to bring an extra rocket to blast off and go somewhere else to, you know, find a big trash can to throw itself away in. So we have to think about other ways to make sure that that spacecraft is super, 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 super clean. And there actually was a poster earlier this week thinking about what's going to happen to something on the surface of Europa. One of the good things about Europa that's bad for spacecraft is that there's all this radiation. And so a spacecraft actually can't survive either in Europa orbit. That's why Europa Clipper is going to orbit Jupiter rather than Europa, so it doesn't get fried by radiation. But if you're landed on the surface of Europa, the radiation is going to fry you pretty fast. And fortunately for the case of any Earth microbes that hitchhiked a ride to Europa, the radiation can help you sterilize your spacecraft. So that's one of the things we can take advantage of. And we're also looking at things like how long it really would take a spacecraft on the surface to kind of very slowly sink into the subsurface with its microbes along with it. So we're looking at that kind of stuff as well.
That's why Enceladus is great, because the ocean is coming out, so you just need to take it.
Yeah, but are the giant squid coming out is the question.
But he got a laugh, but it's a real thing. When you're designing a real mission, it's a fantastic opportunity, right?
One more word. I mean, this meeting here at COSPAR, actually people from COSPAR are in charge of writing, the regulations and the rules in order to avoid spoiling a planet or a moon. So that's a big study here at COSPAR. So,
I know you guys are all scientists, and I think it's great. But when somebody says, so we're going to have to crash it into Jupiter, that's the way we do. That's not trivial, you guys. No, it is. And we're going to fly by, we're going to scoop up some stuff and bring it back. But the thing that's happening in planetary protection, and I apologize again, is realizing that if you land on Mars, you're not landing in the equivalent of a rainforest in a tropical area. You're landing in a pretty sterile environment. And the study that was recently done, or the discussion that was recently took place, people talked about the Viking landers. And in those days, for the young people, it was the height of the disco era. In those days, money was not an object. They even used special metal recording tape This is when the word tape referred to a mechanical tape that could withstand these very high temperatures of sterilization. The way budgets are right now, that almost certainly is not possible. So we have to be just sort of, I would call it more sophisticated about planetary protection. That's an excellent question. Thank you. Thank you indeed. Yes?
Hello? Yeah, so coming from a biology background, I'm actually curious to know since all of you are looking for life forms in different ways, where do you draw the line when you say you're looking for life? Because say if you consider things like viruses, if you consider extremophiles, that would definitely vary what you look for when you say you're looking for habitability or looking for life forms or any of that. So could you comment on that?
When we're looking for life on places like Europa, we're really looking for anything that could possibly survive. So things like extremophiles, things like the microorganisms that live deep buried in rock or in hydrothermal systems that are completely independent of the sun, those are kind of our best analogs for what we're looking for. But yeah, it's always possible we could find life that's not as we know it.
So the word extremophile, if you are an extremophile, you're a normal-phile. You know, it's just a charming human construct, right? I mean, those organisms, whatever they are, just think it's fine where they are. And
You're just happy to live inside a rock.
Yeah, who wouldn't be?
Okay.
But I think to your question, right? You're asking, in some sense, what is the definition of life to some extent?
When you look for extraterrestrial.
Yeah, and so I think. This is one reason I'm a big proponent of searching for life in multiple places in multiple ways. With Sarah Seeger's research, we have atmospheric spectra that may constitute biosignatures if we can rule out all the abiotic bands, and then we have to figure out what it is that's producing it. I mean, maybe we're finding microbes in Enceladus plumes or Martian waters underground or European subsurface oceans. And that's kind of what we're looking for, but this is where your work in life sciences can inform us of what to look for, because maybe you can tell us how we look for viruses on these other worlds, how we detect them. I'm not sure what the answer to that is. Maybe you know. And so we'd be happy to broaden our definitions of biological, but it's challenging, right, to figure out what to look for.
And I love the example of viruses, because you get the right biology teacher and he or she will say they're not alive. You get the other one and he or she will say, well, of course they're alive. Yeah, you idiot. And so this is a fascinating thing. You tell us, man, what is a living thing? Sir, over here.
Thank you.
Thank you.
So the little mini probe things with the sails and the laser beams that are powering them to go forward, how do those work? I mean, is it light or?
Good question.
So.
Good question.
3 years ago, the Planetary Society launched our light sail spacecraft. But seriously, guys, this is extraordinary. And 2005, JAXA launched, 2010, JAXA launched the Icarus spacecraft. And this is an extraordinary thing. But light, although it has no mass, doesn't weigh anything in gravity, it has momentum. And so if you have a low enough mass spacecraft out in space, it gets a push from sunlight. It's crazy. I mean, I admit at first it just seems extraordinary. But we flew one 3 years ago. We hope to fly another one after October 30th. And then anybody work on Messenger? I had a good friend of mine, Deepak Srinivasan, said that you got 5 extra orbits, is that right, by exploiting what people call solar pressure. It's really something that you and I here on the Earth's surface cannot feel. It's tiny. It is about, on a square meter, it's about 9 micronewtons, 9 billionths of the weight of a stick of butter. But it's tiny. But in space, in space, the light shines on the spacecraft night and day. Except in space, there's no night. Whoa. And so with this tiny push, continuously, it can send the spacecraft to higher and higher orbits. Now, for those of you who want to star shoot, I'm all for it. But when you get 5 gigawatts pumped onto spacecraft, you're showing up in some other star system with a pretty good fraction of a nuclear weapon worth of energy. So let's think that through. Let's just be sure we think that through. And I hope you are part of that mission, my friend. Carry on.
So, but if we can just use sunlight, why do we need to use lasers?
Well, the lasers would make a higher intensity beam of light.
Oh, to make it
directed in the
faster.
perfect direction. Directed in the direction, yes. Directed properly to give it a push. It's an extraordinary idea, you know. I mean, think about it this way, there's no sort of asteroid or comet that we can detect that gets that kind of push, that sort of large fraction of the speed of light push naturally. So by collecting energy from the sun, storing it somehow, let's say in batteries or in fossil fuels, and pumping enough electricity to make enough laser light, you could hypothetically, theoretically, give the thing a huge push. It is a cool science fiction idea. And as Dr. Sager says, the line of what's crazy keeps moving and moving. So I hope a guy like you is part of that mission. Go for it.
Couldn't you just like put a magnifying glass to magnify the sun?
So you think about that, and we're going to move on, but think about that. No, but hang on. A magnifying glass and a telescope have the same problem, and they can only collect as much light and focus as much light as they are big. The difference between that and a laser is a laser takes, let's say, solar energy collected from zillions of solar panels. Zillion is a big number of solar panels, and makes it into electricity. Then we use that electricity to generate a very focused beam. We take a very, very large area, a telescope the size of, let's say, here in the US, the state of New Mexico, and concentrate all that light into a beam the size of Pasadena, let's say. It would get a tremendous intensity. That's a cool question. You're thinking big, man. It's good. Over here.
Hi, my name is Jolie Manassian. I'm not a scientist. I'm just an undergrad from UCSD. I just had a few things to say. Dr. Seeger, like, you're the best soccer mom ever. If you're a soccer mom, like, coolest soccer mom ever. And I just wanted to say the second and the third panelist, the kind of shade that you guys were throwing at each other with Mars and Europa is what I live for. And then...
Now, the shade is a different mission, but yeah, I know what you're saying.
Yeah. And then I just wanted to say the fourth panelist, you and Dr. Nye are like besties, and it's my goals, honestly. And then... Mr. Nye, I just wanted to tell you that from like me being small, you kind of inspired everyone to get into science and do all that. And I just think that that's like awesome that you broadcasted it in such a nice way.
Thank you. Now, thank you. Do you have a question?
I do. I have a question. I was going to say that between panelist 3 and 4, I want to hear some shade. I want to see which monster would be better, and why it would be better for the human race to associate with the Europeans or
Europanians, let's say.
Yeah,
Europans.
I need to know this question.
Well, I have to speak for Europa, because again, it's my favorite place in the solar system. You know, Enceladus, to throw some shade in this direction, it's this little tiny thing. It's like this big, okay? It has no excuse for having these giant plumes of stuff thrown off into space. I don't know what it was thinking, okay? Europa is this, you know, it's like the size of the moon, so it's like a good, you know, world-sized body. And it's got this giant ocean, and it's, you know, it's sitting there, it's minding its own business, the life down there, it's not showing off. It's not showing off by throwing stuff out into space. You know, it's doing its thing. So I got to tell you, Europa is really the place you want to go.
Christoph, you're under pressure. Take it.
Europa has more pressure.
Well, what's great about Enceladus is we have so much data on Enceladus that we know that it's like the terrestrial seafloor. And what is very exciting is that on the terrestrial seafloor, you know that life has been able to develop. I'm not saying that life emerged, but And I have worked on Europa too, so I like Europa. But what I really like to do is to do comparative planetology and to try to understand how life may have emerged on Earth just by looking at these other places and to know whether the interaction between water and rocks is where life started. So that's looking at Europa, looking at Enceladus. What I meant is that Enceladus is really easy to look at, when you think about how to get to the ocean. But Europa is definitely a place you want to go. And I am working on project on Europa. I am working on MEL probes that would be able to go through the ice crust and to get to the ocean. So, it's like I have 3 daughters. I love them all.
Cool. So this is so fun. All right. So we'll just take all the questions that are standing right now. It's getting out there, so it's cool. Over here, sir.
Yes, coincidentally, my question is related to Europa. If you have to station something on the surface of Europa, it could be a rover or it could be a satellite for several months, what would be the possible sources of energy? Traditionally, solar panel I hear, but given Europa, it could be other thing like tidal or anything idle. So what will be the possible sources of energy on the surface of Europa if you are testing something for several months?
That's a really good question, actually. So the surface of Europa, we're 5 times further away from the sun, so solar panels really are not a viable option. So when we were looking at a Europa lander spacecraft, we started thinking about how you'd power this thing. So like a nuclear power source would be great, but the problem with the nuclear power source is that then you're bringing this like radioactive material to the surface of Europa where, you have this potential fragile biosphere you want to protect. So we kind of stayed away from that idea. It's not completely 100% ruled out from planetary protection, but it's, we didn't want to do it if we didn't have to. And bringing a nuclear power source like it's in the, some of the Mars rovers, like Mars Curiosity has one of those. They're great because they can last for years and years and years. But on Europa's surface, the rest of your spacecraft is going to get fried by radiation in like a month or 2. So there's really no point in bringing all that mass and paying the tax and all the fuel to bring that mass to the surface of Europa when it'll outlast the rest of your spacecraft. So the Europa lander spacecraft actually just uses a battery. So it's a primary battery kind of mission in its current mission concept, where you just, you have a full charge when you land and you have enough power to last for about a month, and then you're dead. But your spacecraft, so you basically bring enough batteries so that by the time your spacecraft is fried, you run out of batteries anyway. We did look at some other interesting power sources, like, for example, trying to use that radiation. We looked at, well, what if you just built a giant antenna? Could you actually harness power from Jupiter's magnetic field to power something on the surface? The problem was you'd need to bring an antenna that was something like 10 kilometers long, and that's kind of big. So that's one of the crazy ideas that we looked at, and we said, yeah, not really feasible. So maybe the future European civilization will be able to use power sources like that.
That's engineering. Yes, here we go.
Speaking of engineering, I'm an incoming graduate student in aerospace engineering, and by that, I'm interested in trying to develop technology that will better enable new science. And in the context of this talk, to any and all of the panelists, what new technology do you see that, if developed, will enable the next generation of finding aspects of life, whether it's biosignatures on exoplanets or on Europa, Mars, etc.?
I'll start out with something that's maybe not aerospace engineering, but systems engineering. And, I think one of the challenges of planetary exploration is mission size and cost and risk tolerance and how you balance complexity of your spacecraft with the amount of money it's going to cost to land it safely, right? And so I would love for the next, the next 30 years, that'll be the heart of my career, I would like to see us explore more places, because then we wouldn't have to battle about, is it Mars, is it Europa, is it Enceladus, is it more exoplanet missions, is it Venus? We would just be able to go there. So if you can solve the systems engineering challenge of figuring out how to build spacecrafts that are, let's say, 95% reliable, but maybe we can build 200 of them. So if we lose a few, that's fine. That's what I want to do, because I want to explore more. And I think that's one of the grand challenges.
So we'd have, this idea of the CubeSat, 10 by 10 by 10 centimeters, just emerged sort of organically in the community. And so I could easily imagine a spacecraft that would be 1 by 1 by 1 centimeter, a very small but very capable suite of instruments. And a long time people have talked about so-called micro rovers on Mars that would have this capability. And then this extraordinary idea of the quadricopter for Mars. If you had enough of those, to Bethany's point, maybe we could find something really fast and cheaply. Yes, here we go, in the blue.
Hi, my name's Sam Glassner. Thank you all for talking. You guys are all freaking awesome. My question is, if we have tests finding our exoplanets, we're going to need bigger and better telescopes to find, get even closer resolution images. And right now, if we want to send things up into space, we kind of have to fold them up into a fairing and then deploy them really nicely. So I wanted to hear about what your thoughts on in-space assembly are.
Okay, let's see. Well, I think someday we'll have to do it. That's my main thought on it. Someday it'll have to happen, because as we go forward, as you say, and want to find more and more things, unless we have a way to do interferometry, we'd like to do in-space assembly. I support it.
But so the thing about in-space assembly, though, is that, if you picture it in your mind, you're picturing astronauts out there with giant wrenches that are screwing together all these giant folding mirrors. It's probably going to be done by robots. Sorry.
Well, and I'll just say two things. Yeah. The first is, I know some of you got sent away from the mic, so if you want, come up later. We'll stick around to answer your questions. And two, I'll just say that some of this self-assembly of components is actually happening right here at Caltech. So wrapping back to some of the beginning theme, there's lots of innovation here in Pasadena. There's actually a small sat mission from Caltech that's looking to do on-orbit assembly with these tiny little CubeSats called AREST, A-A-R-E-S-T. You can read about it. It's pretty cool.
And by the way, this sort of technology may emerge from oceanography. What the people that explore the deep ocean are able to do with robots that find each other in these super dark environments is really fantastic. And so I wouldn't be surprised if these technologies merge. So the best is yet ahead. This is the last question from this side. You're the penultimate.
No, he's the...
Oh, hold it. You work here.
Yeah.
Sorry, man. Hey, thank you very much, you guys. Thank you so much for coming. Rosalie, take it. Rosalie, are you going to say a few words?
Now I'm just going to thank all you guys and say it's time to close up. So thank you.
Thank you, and good moving Terminator. Great.